Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this homework problem, you were asked to indicate whether the following pairs of molecules are identical structural isomers or geometric isomers. So let's begin by drawing the first pair of molecules and see what we can come up with. The first pair possessed a chlorine bound to a double bond. And then we had an H and a CH2Cl. So there's the one. And on the other side, we have HCCl, double bond CH2Cl. Okay, let's compare these two molecules. Well, we can begin by examining to see if they qualify for geometric isomers. If they're structural isomers, they should be different. That is, the double bond should be located in different positions. So we can check to see if they qualify as geometric isomers to analyze the name. Structural isomers would have different IUPAC names. They would be different structurally. Well, what I have here is a 1, 2, 3. That's a propane. It looks like a 1-propene. And then it looks like this chlorines at 1 and 3. This looks like a 1, 3 dichloropropene or prop 1E. What about the molecule on the right? If I count it, I got 1, 2, 3. It's a propane and 1-propene. That checks. And then we have a 1,3-dichloro. So the fact that the IUPAC name is identical means that structurally these two molecules are the same. And so we can rule out structural isomers. Now the question is, are they identical geometric isomers? To have geometric isomerism, we must look at the carbons of the double bond. We split the molecule and we examine one side first. This carbon, the groups off of it, are they different? Yes. How about the other carbon of the double bond? Does it have different groups? Yes. Come over here, different, yes. So what this indicates to us is the potential of having geometric isomers are possible. Now the question is, in going from A to B, did I draw the same molecule a different way, flipped or upside down, or did I actually create the geometric isomer? Now to answer that question, we can look at the EZ prioritization, or we can search for cis and trans if it applies. Let's do EZ on this structure A. If I look at the first carbon on the left, chlorine's higher atomic number than H, so it's higher priority. If I look on the right, I see hydrogen and carbon. Carbon's higher atomic number, it's high priority. We see our high priority groups on opposite sides of the double bond. Do you recall what isomer that is? A is E for entgegen. Now the question is, did I draw its geometric isomer on the other side? Did I draw the Z? Or is it also E? If it's also E, just drawn in a different way, flipped or tossed upside down, then it is the same molecule. It would be identical. Well, if I prioritize again, I get chlorine higher priority than H, carbon's higher priority than H, and again, I see the two priority groups on opposite sides of the double bond, so it is E. So there we go. Two E's. Well, clearly, this suggests that A and B are identical. And the correct answer for the first question was identical. Okay, let's move on and try the next pair of molecules that we were given this question for. And so, what we have here is an alkene again. And we're going to compare it to this molecule. Now, if I was just doing this quickly at first glance, and I wasn't going to check it thoroughly, I would say, oh, I have two alkenes, and look, the same groups are on the same side, the two ethyls, the two H's on the same side. This is cis. This looks like a cis molecule. And the H on the opposite side, so this guy looks trans. And I would immediately jump to the conclusion that they're geometric isomerisms. The geometric isomers, sorry, possessing geometric isomerism. Now, what's interesting is you got to look a little deeper. You really should look at the IUPAC name just to make sure. For these to be geometric isomers, they must both have the same IUPAC name. They have to have the same structure. They just have to have a difference due to hindered bond rotation. But if the structures are different, yes, one could be cis, one could be trans, but they are not the cis-trans isomers of each other. And that's the question we have to check. We have to make sure that they're cis and trans of each other. And if we do this, if we do the simple name, we've got 1, 2, 3, 4, 5, 6. This is a 6-carbon alkane, that's a hexane, with a double bond at carbon 3. This looks like hex 3-ene. This molecule has 1, 2, 3, 4, 5, 6 hexane. Hexene looking good, but this time the double bond appears at carbon 2. This is hex 2-ene. Given that we have a hex 3-ene and a hex 2-ene, they are not the same molecules. They are structurally different. The structure varies not in hindered bond rotation, but where the double bond is. In this structure, the double bond occurs at carbon 3. In this structure, the double bond occurs at carbon 2. Because they are structurally different and the position of the double bond is different, they are called structural isomers. And so structural isomers is the identification for the relationship between the second set of molecules that you were given, the second pair of molecules. Well, let's take a look at the third pair. And I believe you were given the following. Wow. This looks like a complicated diene. And the second molecule of the pair? Oops, I misdrew the first one, didn't I? Sorry about that. Gotta watch more carefully. Yes, that's better. Okay, here we go. Well, let's just check to see if they're structural isomers first. If they're structural isomers, they should have different IUPAC names. They should be different structures. Indeed, I can do a quick IUPAC name. 1, 2, 3, 4, 5. This is a pentene. 2 enes, pentadiene. 1, 2, 3. This is a 1,3 pentadiene, or penta. 1,3 diene. And you may wonder why I'm doing these names. I mean, I didn't ask you to name them. But the IUPAC nomenclature is quite nice. By checking out the name, if they are the same structure, they have to have the same name. If it's only the stereochemistry that's varying, the change in structure due to hindered rotation about a double bond, that will stand out because both molecules will bear the same name. If I look over at the second molecule, 1, 2, 3, 4, 5, it is also a 1,3 pentadiene. And so the single name applies, so they're not structural isomers. So now the question comes across, do we have geometric isomerism, or are these identical? And so, you know, we can check our rules. If I split this double bond, and I look at this carbon first, I see it as two identical groups. If a carbon has two identical groups, that double bond cannot have geometric isomerism. So the carbon-carbon double bond that has the two H's off the end has no geometric isomerism. Let's check the second double bond. Okay. So if I look at the left-hand carbon, that is this carbon. Okay. I have an H and an alkene. Are they different groups? Indeed. I have an H and a methyl on the other side. Are they different groups? Indeed. So this carbon can have EZ isomerism. Now we can quickly see that the H is a cis. I can prioritize. Carbon is higher atomic number than H, so he's high priority on this side. Carbon's higher atomic number than H, he's high priority on this side. So this guy is Z. If I check the other molecule, I'll see I have a C double bond C, where off one end of the double bond there's two identical groups, two H's, so there's no EZ isomerism there. If I go to the next C double bond C, I have the alkene and the H and the methyl, so it's geometric isomerism. I can prioritize at one end. Carbon's higher atomic number than H. The methyl carbon is higher atomic number than H. My high priority groups on opposite sides, this is E. They're both penta 1,3 dienes. You have the ZE relationship. These two are geometric isomers. Now, as your stereochemistry knowledge grows, we'll be adding new terminology and new isomers to compare, so questions will grow. While this question asks, were they identical, structural isomers, or geometric isomers, we may, for example, later on add to this the pairs conformational isomers. We may add other forms of stereochemistry that we have yet to cover. So this type of question can grow, and you're going to see more of them. Make good quiz questions. All right. I'm Dr. Brian Lloyd. This is my Scribblecast. Thank you very much.